So we started to talk about online learning, optimism in the face of uncertainty as the way to go in this finite horizon setting. I'm not going to go through all of that again, but we should quickly remind ourselves how far we got. So we said that, okay, we're going to have this MVP, state space S, action space A, and transitions P star, and rewards R. Rewards are known, and we're going to estimate the model and then choose optimistically the model. So the models from the setup plausible models, the setup plausible models is C of K, and these are centered around the empirical estimate of the transition probabilities with respect to one norm. We allow some deviation around these empirical estimates up to some radius that depends on the visit counts of the state action pairs. And then we say that, okay, like we need to figure out how big CK should be, how big this beta, this radius should be, how to choose that, and then let's bound the regret. And for the first, like Markov property, all that, Hovding, some union bounds here and there, we calculated that if we choose beta in a certain way, then with probability, the designated probability that appears in the expression for beta, like the confidence sets, all of them are going to include, so simultaneously for every K. K was the number of the stage index where we are in the episodic process. P star is going to be included in this confidence sets with this probability 1 minus data. So that's great. And then we said that, okay, we're going to do the calculations mostly on this set, the good set, good event, where P star is included in this confidence sets. And then we want to put a bound on the regret. Regret was defined as the deviation between the best that we could have achieved. So that's this V star versus how much we got, which is the sum of these rewards. And then, well, okay, we're going to bound this for every K and then see what the expressions give, and then try to show that this is going to grow in a sublinear fashion in K. And the proof starts by decomposing this deviation into 3 terms. The first term is the difference between the optimal value and the optimal value under the optimistic model. And so you subtract and add that. And then the second term is the deviation between this guy and the value of the policy, because, well, the third term is going to be the remaining term. With this, the value is basically the expected value of the sum of the rewards for that round. So this term acts like noise, and you can deal with that with Hovding's inequality. That shows that the sum of these noises grows with square root K, right? So roughly that's the order of it, and we are happy with that. So it remains to deal with these 2 other terms. And then we said that, okay, well, by design, the first term is upper bounded by 0 because we choose the model in an optimistic fashion, and we are on this special event E, where P star is within the confidence set, and P tilde of K was the model that gives you the best value, the highest value in the confidence set. So of course it gives you more value than P star if P star is also in this confidence set. So therefore, the second term that we are subtracting is larger, so the difference is upper bounded by 0, so at most 0. So it remains to bound not the third term, because we already talked about that, but the second term, With respect to the third term, there was this little story though, that the noises here are correlated in time, but the correlation is benign. It's called a Martingale difference noise. And the inequality that we all learn about and love, Hoeffding's inequality, extends to this case without any change. And so it's useful to know about this Martingale differences. So this is called Martingale difference noise, or Martingale noises, Martingale differences. The sum of the Martingale differences is called the Martingale. All right, and that remains to bound the third term. And if you look at it, it's just like the differences of the value functions of a policy, a fixed policy, the current policy pi k, under two different models. And we have seen this, we have done it. You just start with the Bellman equation, expand the value functions, and then just do some rearrangement. And lo and behold, if you do it, then you can get this form. So for the value function differences between value of policy pi under model p star versus under model p is equal to this guy here plus this guy, and here you have value differences. So this is the same as here, except that there is h plus 1. So that's going to suggest a recursion. And the other guy is just differences between the models, the transition probabilities. And so if those differences are kind of like under control, then we'll be fine. We talked a little bit about that it would be a mistake to take the L infinity norms. Maybe you can try to do that, and then you can convince later yourself that that would indeed not work very well. So we're not going to go there. And so the next very, very valuable trick, which is, well, not trick, but observation, which is going to help us a lot, is to notice that we can get a recursion, a fully blown recursion for these differences if we're focusing at the current states and the states that we visit within the trajectory. So when you apply this value difference identity to our situation, so in our situation, this p is going to be the p tilde key, a pi is our policy pi of k, and we only care about these differences at these states, the sh of k, the state that is visited on the stage in that episode. And so let's denote this difference by delta h of k. And then the observation is that if you take delta h plus 1k, then the first term in this value difference identity is just the conditional expectation of this difference given the information up to that stage, including the state. And therefore, you can write this whole thing, like you can imagine that this is replaced by just delta h plus 1k, and then you have to subtract that and add back the expectation. The difference between that quantity and its conditional expectation. Now, that's again a Martingale difference sequence. So we will be able to apply Hoeffding Azuma again. And indeed, that's what we're going to do. And so this is your eta. So that's this Martingale difference noise. And here is our recursion. And from the remaining term, this term, if we are rewriting it, we're going to boldly take the use Hölder's inequality and basically take, well, you have to avoid, oops, avoid this expression. We have to avoid this expression at s of h of k. And if you think about it, what that means, well, you take the transition probability there, and the action that was used by the policy is deterministic. So this m pi of p star applied to this value function evaluated at that state is boiling down to what is the expected value of that value function. If I start at this stage, I take that action. That is the action that is taken by that policy pi of k. Okay, because it's a deterministic policy. We can name like what it does. It has this name. That's that action. That's what the policy chooses. And so that's just an identity that you can evaluate this expression. Then it simplifies to this form, and then you have transition probabilities, differences of transition probabilities applied to a value function. And so that's an inner product. You can take Hölder's inequality, apply L1 norm on the first term, L infinity norm on the second term. The L infinity norm of the second term, which is this value function, while the maximum range of that value function is h, so that's just h, and so you end up with this L1 norms. Okay. So that's how we get to this point where we have this L1 norm difference. And now we can use that we are on this event E, on this good event. We know that P star is within beta of the empirical transition probability. And the same holds for P tilde. Therefore, by the triangle inequality, they are within of 2 beta of each other. Now, the argument of beta is going to be just like how many times you have visited this particular state action pair. So this goes back to the definition of like what the confidence set was, right? So here we are using that. So there is this beta. Fine, we're going to need this form for the beta. And where is this? Oh my gosh, it's been here. So that's the form that we are using. So the L1 norm difference is at most beta applied to the count. Okay. So we get this recursive inequality, and if you expand the whole recursion, then you get that, well, we were only interested in data 0 and k, so there's this guy, and you expand the whole recursion, all these terms are piling up to h minus 1, and then all these other terms are piling up as well, and we got this inequality. So there were 2 noise terms, and in addition to that, in the regret bound, well, okay, so one of the noise terms is the eta terms, the other noise term is the xi terms. So there is those, and then in addition to that, we only need to bound these guys, like the sum of these over k. Okay, that's what the whole regret bound is going to boil down to. So if you want to summarize, so we can start by saying that R of k is smaller than equal to, so that is the third term, the xi k, xi of k. We already said that, okay, this is going to be bounded by this, so we can just add that. But maybe I just add the xi of k. And then there is this other term, the eta terms. And then there is going to be the beta terms. So now to do something useful as well, notice the form of beta. So beta is some constant times square root 1 over the count u, right? So it's like beta of u is constant divided by square root u. But a constant is going to depend on, well, okay, so if I want to write it, where do I squeeze this? So beta of u is this constant that depends on, I don't know. Okay, so here I also see a u here. Good to zoom in. There's this u. Well, the maximum count that we can ever have for any state action pair is k times h. So just plug that in. You get something bigger. So beta of u is smaller than equal to c over square root u, where you can choose c to be this 2 times the square root of 1/2 s log 2 plus log, and then kh times kh plus 1 sa over delta, right? I just call it a constant. Depends on delta, right? So maybe it also depends on s and a, but and k and h, but those difference that, like, okay, we're gonna remember those, but like at the end when you plug in, then you have to carry the whole expression, of course. But so let's just simplify things by writing this upper bound. Okay, let's go back to the end. The c of delta can come out because it doesn't depend on anything. And then you just have 1 over square root it's when nk is 0, then we have a 1. So, right? So just what I wrote was true for u greater than equal to 1. But what if u is equal to 0? Okay. We can upper bound it by 1 and then by potentially further increasing c data. Well, we have to see whether the c data was smaller than 1 or bigger than 1. Okay, like if s and a are big enough and k and h are big enough, I'm sure this c data is bigger than 1. Then it's still true that, so we want to use here that no matter what the value of u is, for every value of u, including 0, all right, beta of u is smaller than c delta divided by square root u, all right? And we know that beta 0, we chose it to be 1. So I'm talking about, is it true that like this holds? Yeah, it's gonna hold if s is at least, wow, maybe it holds always if you look at this expression. If that, maybe data equals 1 would break it or something like that, but like, okay, if data is bounded away from 1, nah, even that wouldn't break it. I think it holds. But let's just, okay, like at cases like this, all right, so you should make yourself a note that later on, maybe you have to check whether like this holds always, but I believe it holds. And like it definitely holds if s and a are big enough, and k and h. So s, a, k, h big enough, and delta is small enough, then it's definitely hard. So let's not worry about it. And then we can take the maximum between 1 and what was here? Nk of SH K AH. Okay. All right. Okay, so these terms can be bounded using Hovding-Azuma, and then should have the order of square root k, because they are noise terms. And then maybe multiply with h, because the range of the noise terms is h. So let's not worry about those. How about the others? How about this? Like, this is the critical term. So you're going to say that, well, there's no way this is going to be too large. How do we do this? Well, we're going to introduce, so let's call this 4. So 4 can be rewritten as the sum over state action pairs Nk and h of just restricting things to when a given state action pair is visited. Right? So decomposing things based on the state action pairs. And since we have this indicator, we can replace here SAH, S of h of k and A of h of k. Under the effect of this indicator, they're just S and A. Right? So this will allow us to focus on what happens at a particular state action pair. And then overall, we come back to like, okay, what happens overall? And if you look at this, the inside sum, it's just summing up how many times we have visited a given state action pair within an episode. So let M of k SA be the sum of these indicators. Right? Then we also see that N of k is just like the sum of all of this. So M1 SA plus MK SA. So just the sum of all of this. And so the fourth term can be written as with this new notation, with this form. Okay. So if you look at this, this is a very curious form. So let's ignore that we are taking the maximum with 1. So as if this part was not here, like all the counts are already bigger than 1 or whatnot, then it doesn't matter, right? Then what you have is the sum of the counts that are upstairs, they're downstairs, but under the square root. And this must remind you of like, okay, like this looks like that you have a function and it's like, this is the function here. Which is the sum of all of these things. Then if these are the sums, then these are derivatives of the function. And we are integrating this. This is like an integral. The sum over the k, that's like an integral. So the whole thing really reminds us on taking the derivative of a function whose and dividing that by the square root of the function and integrating this over. And this is helpful because if you think about how to integrate this, you can notice that, oh, well, okay. So if you take the square root of the function, then the derivative of the square root of a function, what is that? Well, that's 1/2 times the derivative of the function divided by the square root of the function, right? Which is exactly what you have here. So except that, okay, like there has to be a factor of 2 there. So now it looks like that if this was really integrals, then if we are integrating here from 1 to capital K, then this should be between the limits of 1 and K or whatnot. Then this should be, I don't know, like upper bounded. Things are non-negative here by 2 times the square root of the function at K. Okay. Because I'm just dropping a term that I would need to subtract. Now, of course, this is not a proof. This is just a hunch, given the form of this expression. But you can make it a proof. So you can show that for any, I don't know, m1 to mk, and these are non-negative numbers. If you take the sum of mk divided by the bigger of 1 and the sum of the previous cons up to mk, then this is more than equal to 2 times the square root of m1 plus mk. Right? I'm not going to give you the proof, but The proof basically follows what the hunch suggests. You should look for an opportunity to do some telescoping sums. So maybe split the sum based on whether the sum of the m case is bigger or smaller than 1. And okay, if we assume that they are always bigger than 1, then you just look at this expression, except that like it's not, this is not there. And then you just try to upper bound it in a telescoping way so that you know that you need to get this, right? Like you need to get that, well, basically the integral, the primitive function of this is this, right? Like, so that suggests that you should get the difference 2 times the difference of the square root of the sums of the partial sums up to mk and up to k and k minus 1. And that's just algebra to prove that. So it nicely works out. So proof is just telescoping. All right, so once we have this, now we can bound for using this lemma. So we're gonna have a sum over SA, and then this whole sum, this thing here, can be upper bounded by the 2 times the square root of the cons. So the sum of the MAs is the NK. So, all right. So now we can use Cauchy-Schwarz. So if, or Jensen or whatnot, I like to use Jensen. So that goes by saying that, well, if this was an average, so here there were some weights that sum to 1. And here I have this function, the square root function, which is concave. Then if I move the square root function outside of the average, so here's my average, and I'm manipulating the average by moving the function outside, then I get something bigger. All right. So that's just Jensen's inequality. The only inequality that we ever need. And okay, the SA goes under the square root, and the sum of the cons. So how big is the sum of the cons of visiting any of the state action pairs? Well, it's the total number of interactions with the MDP, which is h times k. So this is h times k. So this whole thing is equal to 2 times SA h k. Right? We're done. So putting things together gives the theorem. With probability 1 minus BO delta. Oh, that's really ugly. But I think 2 delta or 3 delta, and like them, maybe this. C delta here has to be adjusted to, I don't know, like, okay, it doesn't adjust, then it's like, I think it's 3 delta. The regret of this optimistic algorithm is going to be bounded by, well, there is this term that we just got. Is ever multiplied with anything else? These are just the con. Okay, there is the C delta. There we go. So 2C delta. And then there is that too. Well, I'm going to lose track of the constants anyways. And here, remember that this was like, I don't know, there was an S log 2, and there was a log HK SA divided by that, or something like that. I'm dropping constants. So just to give an idea about like how many S's do we have, for example, like how many times do we count the state space? So here from this term comes a linear dependence on the state space, for example. Square root dependence on action, square root dependence on age so far. Yeah, this is just transitions. So, but this was multiplied by age, I'm pretty sure. So, yeah, it looks too good to be true. Yeah, indeed. So there is the age, because we are bounding value differences. So like there should be some dependence on the range. So there is that age. So that should have been copied here. This is how you lose track of things said. All right, okay, but now here we are saving the day by putting this back. So there is an additional age dependence. Plus there are these noise terms. So there was a noise term, the psi. And we said that, okay, that has a linear dependence on age, square root dependence on k, the log 1 over delta. So dropping constants, some other constant. And then there is the eras, and there is what's going on? Yeah, there are all these eras. Ever the eras defined. So here are the eras. So these are Martingale differences all the way. All the kh of them are Martingale differences. And by their definitions and the range of them, because they're based on deltas, and the deltas are defined based on values. And both of these values are between 0 and h. So the range of the value difference is also 0 and h. So the difference between these two guys is at most h. So there is an h coming from these, and there is square root hk, because that's how many terms we have. Log 1 over delta. All right? So that's the theorem. Okay. So is everything all right? Everything the tight is possible? not so much. So there are better results. And there is a very recent paper by Zihan Zhang and Xian. Sorry for completely killing all these names. Simon too. Their theorem is that if the total reward per episode along any trajectory is smaller than or equal to capital R, it could be just like, very small, like binary reward, like one reward at the end. Then it just won this capital R. Then you can show that there is an algorithm such that the regret of the algorithm is going to be big O of R. So everything only scales with the total reward. So that was my age, right? Like I upper bounded everything mercilessly with age. But if the total reward is in a smaller scale, then you can use Bernstein tricks and whatnot to get a better dependence. And this is the result in this paper. And so you get a square root dependence on the number of state action pairs. And there is a lower order term, though, which depends on the total number of state action pairs. And then there is some polylog, which depends on everything. But this is strictly better than what we proved. And this is for an efficient algorithm. The lower bound says that the first term needs to be there. So that's another theorem that says that no matter the algorithm, you can always find an MDP with the set properties such that the regret of the algorithm is at least R times square root SAK in K episodes. So that term is tight. The other term, we don't quite know, but probably yes. This was for the homogeneous case. For the inhomogeneous case, when you have not one probability kernel, but H probability kernels or transition matrices or whatnot. And the reward can also depend on the stage. Sorry, it should go from 0 to H minus 1 is my notation. So in this case, everything gets an extra H, I think, because you have like H times as much data to estimate. So if you're in this homogeneous case, then that makes things a little bit easier in terms of computation, because you can just do backwards value calculation, because there is no sharing of the dynamics between the stages or the rewards. I mentioned Bayesian bonuses. You can get a result for Q-learning, which is almost as good. For this case, for the inhomogeneous case, I think Q-learning is optimal in terms of minimax regret. Well, it's optimistic Q-learning, all right? if you want efficient, so the algorithm we did the analysis for, the question was, what's the name? It's UCRL or UCRL2. And this algorithm was analyzed first in the context. It's based on the model-based algorithm, right? It was first analyzed in the context of infinite horizon case. And the analysis goes back to Yaksh, Ortner, and Auer. And if you want efficient implementation, then oftentimes people randomize. So this optimism can be implemented using randomization. The idea there is that somehow you add random noise, and with high probability, you're optimistic. Then you can push through the analysis. It's going to be more complicated, but it still works. Other type, so the nice thing about this is that many times this randomization can be implemented in a computationally efficient way, whereas the optimistic planning algorithm may be difficult to implement, or we don't know whether it has an efficient implementation. We don't know whether like these argmax can be calculated in an efficient way or approximately closely enough in an efficient way so that the guarantees don't break and we have computational guarantees as well. In these cases, a lot of times you randomize, maybe you give up a little bit on the regret, the constants are a little bit worse. And this is also close related to what people call PSRL, posterior sampling reinforcement learning, or Thomson sampling, which is a special case. Which people like because it has a Bayesian interpretation, and so for some reason people like interpretations. I like results. But it's nice. And we should also mention that like other possible designs for algorithms with regret guarantees, like there are other possibilities beyond this randomization and optimism. Elimination comes to mind. So we talked about that there is this view that there is all possible words, and you can eliminate a bunch of words based on the data that you have seen, and then you have the remaining set of words, this smaller set. And then from there, you could choose optimistically, or you can just like create some cover or something like that, so that like you're guaranteed to gain enough experience. So if you're in a bandit situation, for example, then maybe you would choose like each of the arms which are not eliminated a certain number of times, and then you get information about them. If you're in a structured bandit setting, then maybe you can run an optimal design to come up with some clever way of gaining information about all the arms without choosing all of them, and so on and so forth. So elimination is another way of general pattern of designing good algorithms. And then there is information-directed sampling that was mentioned the other day, and so on and so forth. So I briefly mentioned that this UCRL was done first in the context of infinite horizon MDPs, like never-ending MDPs. Like you go around and you're just like collecting reward, and some people would say that that's the average reward setting or whatnot, but the regret is defined in the same way. And in that case, it's a little bit more challenging to do all of this. And one of the challenges is that, so it's like the infinite horizon case. There are multiple challenges. So one of them is that there are no episodes. There are no natural stopping points. So here in the episodic setting, at the end of every episode, we updated the policies. By the way, we don't really need to update the policies that frequently because the statistics have the property that they change very slowly, right? Like before your cons get really, really different than the cons that you had before, your policy is not going to change much. So why do all this calculation, recalculating the policy to follow before something substantially changed? So that's the idea that you can use in the infinite horizon setting. So that's one idea you can use. So you can say that, well, let the boundary of an episode be when a count doubles. The first time you see that a count has doubled compared to what it has been, state action pair count, like how many times you visited that, then you say that, okay, it's time to recalculate the policy. Or you could a priori also decide about some schedule, like, okay, like every square root, I don't know, t steps, I'm going to recalculate policies. So fix the schedule. That's the other possibility. If you try to update your policy every time and you're playing optimistically, that's a bad idea. You can construct examples where an optimistic policy which doesn't define, so these are not optional, this is necessary, doesn't define these episodes, it's gonna suffer linear regret. So without episodes, you get linear regret with optimistic algorithms. And the problem is that it's like a city two-state example where you can go between two states, and then if you're at a state, then you get the reward of 1, and if you go traveling between the states, you get a reward of 0. An optimistic algorithm looks at the other state all the time eventually and says that, well, it would be better to be there, maybe. And then it goes there, and then once it's there, it says, oh, it would be better in the other state, maybe. And you can design all these things in such a way that the optimistic algorithm just like spends all the time traveling between the two states, collecting no reward whatsoever. Because it always plans for that, oh, like in the indefinite future, it may, this other state could have a little bit more rewarding. I'm not quite certain about that it's not more rewarding, but if it was, that would be a huge advantage over an infinite horizon. So I need to check it out. But if you are checking it out too eagerly, then this results in starvation. So then you're not eating these rewards. Like you need to also eat it. Like this is the example where you want to have your cake and eat it as well. So this is like you need the episodes for eat the cake, right? For eating the cake. All right, so that's a complication. And there are other complications, like if you have an MDP, which is a continuing MDP, maybe it's going to have like this weird structure that like you start in this part of the MDP, and once you get into some other part, there is no way going back. And it could split, like you may you know, like end up here or there, and then there is no way back, and there is no way here, and there is no way there, you either stay here or you're staying there. And at the beginning, when you don't have much information about where the reward is going to be higher, you must choose at one point, and you end up in part 1 or part 2, and like there is absolutely no control about that. So people are kind of amused by this, but I'm not really amused. I mean, like, it's just like life, right? Like, you fall into these traps, and sometimes some decisions are irrevocable. You do whatever is the best eventually. So once you are in this communicating path, in such a path, you should collect as much reward as you can, and we should be satisfied with that. And there is no need to regret of these initial decisions which are happening in an uncontrolled fashion, right? But eventually the algorithm should be demanded that it should work well. But you might be wondering about, okay, like, should an algorithm like this spend a lot of time here before it kind of like leads out or not? Or I don't know, like, yeah. All right. Ooh. Okay. All right. So this is what I wanted to say about these. And in the remaining, how much time do we have? 15 minutes. Let's have some more fun. So what if we throw in function approximation? Like, we want to scale up things. So let's throw in some function approximation. So back to the finite horizon setting. I'm almost certainly not going to be able to get to the full proof for this, but so let's say someone gives you function approximator with state action features. As usual, things are bounded, blah, blah, blah. And you have a horizon of age. Maybe it's the inhomogeneous case. So then maybe the function approximation, the feature extractor is going to be indexed by age as well. Doesn't really matter. So how can we use these function approximators? Well, one idea is somehow approximate the action value function, the optimal action value function. So kind of the hope is that Q star would be in the span of the features. We'll see that we'll need something more than this to make these algorithms work, or the algorithm I want to talk about work, but that this is the starting point. So somehow, if this was the case, so somehow we are shooting for a case when Q star may be lying in a span, then one idea could be to have an algorithm which tries to compute upper bounds on Q star and then act greedily with respect to the computed upper bounds, and then just repeat this. So the idea is, let's get upper bounds, upper confidence bounds, UCB on Q star plus greedy. And when computing the upper confidence bounds, somehow we want to use the features. So we're going to mimic as if like, oh, everything is kind of linear. So let's just run our regression thing. So how does this work? As before, we're going to have these trajectories for the case episodes. The data is the same. And then we're going to use the features to do this calculation. We'll do the following. We're going to construct these functions. Using some weights with the feature map that we have. Yeah. And then we reserve the right to do other things. Okay. So we are going to assume that we know the reward. So we're not going to approximate the reward function. So the rewards are known. Okay, so since the rewards are known, we are not kind of regressing. So normally, so what happens with the optimal value function? The optimal value function satisfies that it's equal to the reward plus the transition, and then you look at where you can get, and what's the optimal value there. So that's Bellman's equation, right? And so if you have, for the subsequent stage, some estimate, some upper bound on Q, then maybe you can get an upper bound on V star by just maximizing with respect to the action component, right? So for every age, including h plus 1, just define V of h of k as this maximum, because, well, we knew that this was the case for Q star. So basically mimicking value iteration. So this would be value iteration, right? And we don't know the transition probabilities, right? So we're going to use the features to use the data to approximate the effect of like this averaging would do over the next states. And so since you have the data there, we are in episode K, and we're at the beginning of episode K. Data up to K-1 is available. Then we're going to do a least squares fit to try to fit with linear regression on the next states under the data. So the W of h of k is going to be the argmin of the W's of the loss. We take all of our data and we look at where we have been. Okay, so let's introduce this z of k of h, which is just the state action pair at a given episode in a given stage. So I can write less. So we are trying to use the features and the weight to predict what the value is going to be. Oh, and here I should use I. So these are the previous episodes. So in the previous episode, we had this sorry, the I is an upper index there. And here I can write, let's say, we already done the calculation for this episode, so the most recent information is based on just the latest value function. And then let's also add some regularization. So that's our W of age of k. But there is a little problem here. We said that we want to calculate upper confidence bounds. Why do we want to calculate upper confidence bounds? The reason is simple. We want to be optimistic. And as we will see, if we have upper estimates of the optimal value function, then the regret decomposition that we had before is going to work the same way. Like, we can basically repeat the same decomposition as if we were estimating a model. It doesn't matter whether you were estimating a model or not, or you just chose a value function that was an upper bound on the true value function. It doesn't matter whether that value function came from choosing a model or not. The regret decomposition works the same way. So we had this term 1, term 2, and term 3. You remember? We can go back here and then imagine that you just came up with some way of some value estimates, and then this is an upper bound. Then, of course, this is going to be less than equal to 0. And if this was not based on a model, then you will have some work to be done when executing the recursion that we had before. But that's the work that is going to be left. The rest of the decomposition, all the noises, everything, it's all the same. So that's the only part of the analysis that you need to worry about, this recursion. Okay. So that's why this is a plan, but we need to ensure that we get an upper bound. So we're going to add something here, beta of k of h, which is some function that we're going to choose in some way so that this is an upper bound. So beta k of h to be chosen later. So this algorithm is called when instantiated in a particular way. And okay, there is one more thing. Here you would truncate. I think you truncate here at age. So if the value, like the predicted value, is ever above age, then you just say, no, it's age. This algorithm is called LSVI UCB, and was quite recent by Chi-Chin, Zuran Yang, and Zauran Wang. And Michael Jordan, the other one. Okay, and so based on what I said, you can see how this analysis is going to go. So the question is how to choose this beta. Is it going to be too big? And like what other terms are going to show up in the regret bound? So for least squares, so there are a number of things. So we have done the analysis of least squares in some other setting where we were doing planning. And we have gotten some upper bounds on how much the least squares estimate deviates from the true function when the actual function was linear in the features. So one assumption that can help us, and it's not really necessary to make this assumption, but if you don't make it, then there's some approximation errors that come up, with which you can still analyze the algorithm. But a helpful assumption that people often make is that if you take whatever functions that you might encounter, like, so here we are doing linear regression based on these targets, right? Like the transition kernel applied to some function. Actually, the functions that we're applying to have this form. So the true reward plus some linear stuff plus some beta stuff, which we haven't said what it is, but like it has some specific form. So if you collect all those functions into this function set V, it's going to be a subset of all the functions over the state action pairs. And you assume that for any of those functions, if you apply P of H to E, then you get something that's linear in the features. And this holds for every H. Then you are indeed in the realm of linear regression. Then you are rightly applying linear regression tools. And the previous analysis that we were doing wouldn't quite apply because we used too much IID, blah, blah, blah. And here we don't have IID because all the data that comes is serially correlated because it's generated by the algorithm. But the nature of things is still that there is noise. Okay, this noise is martingale noise. But we already discussed that martingale noise is not so different. So by and large, the tools extend. Sometimes it's a little bit tricky to extend these tools, and there are some open questions surrounding like tight bonds and whatnot still in this case. But for linear regression, you can state things like, if you have some basis functions phi, and you have some data, let's say x1, I don't know, x, I don't know, n, and you have these targets, the y1, yn. So these are, I don't know, these are the feature vectors themselves, let's say. So they are d-dimensional, and these are the targets, they are just reals. And it holds that the yt is equal to, I don't know, xt transpose and some theta plus some noise, where the noise has some convenient properties. So it should be sub-Gaussian. So if you condition on all the past, then this is, I don't know, like, it has this moment generating function, which is very convenient. So that also means that it has zero mean. Then if you're running linear regression, least squares regression to get estimates of theta, so how does it work? It works by fitting to the data, plus maybe you have this regularization term. Then actually this can be an infinite sequence. So it's like this result holds for infinite long sequences. Then with probability of 1 minus delta, it holds that your predictions are going to be accurate if you're predicting with this regularized least squares estimate for any x uniformly. So it doesn't matter what x you choose. If you try to predict at x of what you should be getting, which is the inner product between x and theta, then this difference is upper bounded by, okay, and here comes our old friend. The old friend is just the moment matrix up to a given time point. So this is like xs transpose plus lambda I. So the moment matrix times some function of t and delta there. So this term is the familiar term. So that was the same term that we had before. So we have seen this, that like that's the uncertainty. And this beta t of delta I will not know off the top of my head, but it's just like some log determinant business. It's like
hello, Tilo. Oh, hello.
plus, I don't know. Let's make this theta star. This is theta star to norm. Yeah. Right. So you have this lemma, and so this suggests two things. So one, if you want to get upper bounds, then you should choose this beta in the form that involves this term and maybe a coefficient like this, maybe slightly increased. That's up in the air. That's one thing. The other thing is that, okay, how are we going to do the telescoping argument? So to do the telescoping argument, it is worthwhile to recall a bunch of properties of linear least squares. So linear least squares can be viewed in many different ways. Actually, you can view the whole thing as trying to estimate. So here, the target, like I can define, maybe it would have been better to do this for some arbitrary v, okay? So I'm going to just plug an arbitrary v here, okay? And then say that in the algorithm, we're gonna use this specific v, right? So in the algorithm, the specific weight is going to be just for v of h plus 1, okay? You're applying it at this point. So the useful thing here is that if you think about how this works, so if you have a function, you can assign to that a weight. You can assign to that a function too. So this is like an operator. Takes a function, returns this other function. And you can view the whole procedure as approximating pH of v, because that's what it does. Even better, this is linear in v. That just comes from the properties of like how least squares works. So you can write explicitly how least squares looks like, and you will see if you're expanding the definition, the least square solution is linear in v. If I move V a little bit, like the W moves linearly with it, right? If you recall the definition, or like the solution of the least squares is going to be the bias moment matrix inverse times the sum of the correlation of the features with the data, the targets. The targets is the V. So it just appears linearly. It's beautiful. So this whole thing is linear. So this is just a linear operator. So this guy here is a linear operator. So let's call it PH of K applied to V, right? We're in business. Because now you can do all your telescoping. So we just reinterpreted least squares as giving you operators and approximating operators, because it does that for you automatically. And then you can rewrite the whole, like you can repeat the steps of the previous proof. Nothing really changes. Okay, you have to be a little bit more careful with these upper bounds. And this lemma alone is not quite sufficient. You have to work a little bit more, because this applies for any fixed target function theta star. And whenever we are running our algorithm, this V of H plus 1K already depends on the data that we are using in the least square solution. So there are correlations there. So that's a little bit of complication, but those correlations are pretty mild. So you can use whatever is called covering argument to argue about that these correlations are not going to hurt you too much. You have to increase a little bit your beta because of these correlations, and then you're done. And at the end of the day, you can prove that the whole thing works. And the proof basically repeats whatever we have done with these modifications. This is nice because it also shows that, okay, like the arguments were not worked out for the functional problem, but they are pretty close to that. The root of the argument remains the same between the functional approximation and non-functional approximation case. And also this procedure is computationally efficient. You just compute these least square solutions. These betas are given in closed form. Nothing is like really too complicated here. And you get this nice result. All right. I should stop here. I would definitely add this also to the write-up of the lecture notes. There's so much that I couldn't talk about. In connection to online learning. So there are a lot of alternative designs, a lot of other results. For the things are way more difficult when you have functional approximation and you're in online learning and you have infinite horizon. Then I think that we don't really have satisfactory solutions. We have a bunch of proposals. It's a very interesting question. All right. Yeah, so there are so Alex was asking whether Domru's work would be on, well, he has multiple works, but I think that those are for special cases. So today, okay, so I didn't call this in a name, but so this could be called a closeness assumption that, well, it's more than a closeness. Well, it's kind of like V can be a little bit larger than this function space spanned by the features. If they were the same, then it would be called a closeness assumption, but this is a little bit stronger as an assumption because V is like linear functions plus bonuses, and then those are mapped back to linear functions. That's kind of the the underlying assumption. And so this is called the linear MVP assumption, that somehow the probability kernels, when they are acting on functions, then they just map everything into linear stuff. So they have a low rank factorization. So transition kernels can be written. Oh, by the way, like you have seen this in one of the homeworks, right? When we were exactly in the planning setting, we were analyzing least squares by iteration. So this is basically repeating the same things on steroids because it's more complicated because things are correlated in time. But back to the question, Dongru's work is for linear mixture models, I think. So that's a different setting. So here, there is some assumption made about the model, the transition kernel, but it's not like that it would be finitely parameterizable. And if you have like a finite linear parameterization of the transition kernel, then that's like great. Then you can run these model-based algorithms. We also worked with Alex, is first author of that paper. We worked on this too, and it's also fun, and it's an alternative, so a complementary model. Like none of them is more general than the other. So if you want to study, my impression is that if you want to understand model-based RL, then maybe that's a good starting point, these linear mixture MDPs. And if you want to understand more about the model-free setting, then this linear MDP assumption is your friend. Yeah. Yeah, thanks, Alex. All right, so this was quite compressed. Thanks for hanging out up to the end. Next week, we are going to have awesome presentations about the project. We will need to get organized on the Slack channel. I guess we can do that there on the private channel of who is talking when. I guess everyone wants to talk on Tuesday and no one will want to talk on Thursday, right? Shall we randomize?
Maybe we give an incentive, like you get a like an extra point if you present earlier than others. Or maybe we grade you.
Where the meaning of an extra point is not defined, but it's a nice touch.
Yeah.
Or randomize. Or exploration bonus.
So Connie, do you want that exploration bonus?
I guess an idea of maybe you can stop recording.